Hello, my name is Andrew Montcherraju, and this is Lab 3 for Physics 2212. The purpose of this lab will be to test the strength of a bar magnet and model the magnetic field using GlowScript. We'll also observe the relationship between the distance the magnet is from a magnetometer and the magnetic field strength, and we'll also be modeling the off-axis magnetic field, as aforementioned, in GlowScript. The results were that we had a value of n, which is essentially a value. It's an exponent for r that is of negative 1.3357 and a magnetic dipole moment of 27.166. These are both rather. This is the magnetic dipole resulting from a rather small value of n, but we'll get to why there could be a potential error there. But some equations that will be vital to this one would be the Biot-Savart law, which I wrote this out twice for an on-axis dipole and the off-axis. On axis, we can simplify it up to saying mu naught over 4 pi, which times 2 mu over r cubed, r being the distance, mu naught being a constant, and the mu is, this is a constant specific to, mu naught's a universal constant, while mu is just a constant specific to each individual magnet, which we will be calculating, and we'll be calculating it with the distance dependence equation of the magnetic field of the bar magnet equal to k times r to the nth power, n, which we will derive from the ln of the magnetic field of the x component being equal to the natural log of k plus n times the natural log of r. We have to use this experimentally, but we'll get to all that soon. And we have the off-axis dipole, which we will be using this equation we'll be using this equation as the one that will be informing our formula. You'll see this later too. So the procedure is we download the magnetometer app on our phone, and we locate the magnetometer chip in the phone. Then we align the phone to the magnetic north, thus ensuring that the Earth's magnetic field will not impact the experiment too much. To determine n, we just had to test the magnetic field at several different distances and plot the distance against the magnetic field. And then for the off-axis magnetic field, we have to measure the perpendicular magnetic field and distance, measure the magnetic field to the Earth, and calculate mu using the perpendicular magnetic field and the equation. The initial condition of such will be that that the system is the cell phone, while its surroundings would be everything else around it, as we're assuming that the forces are acting upon the magnetic chip. The magnetic field of the Earth is going to be approximately 49 microteslas, and no electric fields will be affecting the measured magnetic field. This is an assumption that we'll be making for now. But here are the results all laid out. I'm not going to go into depth on each of them, but essentially, all you need to know is that that equation on the line of best fit curve corresponds to the equation, the distance dependency relationship earlier. We can see what ln of k equals, meaning that k itself is equal to e to the negative 12.123 power. Well, we can derive n from here, and r we're going to set equal to 1. R being essentially arbitrary right for now. Then we can use this to determine the value of mu, being 27.166 amps per meter squared, or amp centimeter squared. And basically we just set the on-axis dipole formula equal to the magnetic field of a bar magnet to find mu. Now, some observations you notice here would be that that when I was measuring it, the magnetic field in the x direction when you brought the magnet far away from the cell phone was that it was pretty much stabilized at 21 microteslas. And as the distance between the magnetometer and the magnet decreased, the x component of the magnetic field increased greatly, and you can see that on the graph as shown before. Now, the coding section, for the magnetic dipole, we had to use the off-axis formula, and this entire coding section, it's pretty much just trying to continuously measure the magnetic field at different locations, perpendicular to it, parallel to it, and the net location, which we can see illustrated right here with the orange arrows being perpendicular. The orange arrows which are pointing on axis, the blue arrows pointing off axis, and the purple arrow pointing as the net. Now, some errors were the interference from other magnetic fields, which I believe probably impacted my final results greatly. There probably was some other magnetic fields in the lights. Another one probably not aligning the phone with the magnetic north pole. This will be affected. This will be affected by interference from other magnetic fields, and also not properly aligning the magnetic chip with the bar magnet. I had a struggle with trying to do this, and I feel I probably got it slightly wrong for it. And that probably is what caused my results to be very inaccurate in this instance. Now, what if you hadn't oriented the experiment to conflict from magnetic north? The Earth's magnetic field would be, well, this kind of might have happened in my experiment, where basically it's going to be inaccurate because the Earth's magnetic field is actually impacting the results, whereas before we could assume it isn't. Now, if you were to stick two identical magnets together end to end and run the experiment again, the magnetic force should be larger, as adding a second magnet would be the same as doubling the size of the original magnet. So, thank you for watching. Have a great time.